Hello. In this video, I'm going to show how to solve this problem involving friction and a spring. Okay, so we have a box of mass m, stationary on a surface, coefficients mu(s) and mu(k). Person is pulling on this box. Spring with a spring has a natural length L0 and a spring constant k. So the first question we want to answer is how long will the spring be when the box begins to move? Okay, so the first thing I'm going to do is draw a picture of a box here, mass m, it's on a surface. I'm pulling it forward, force, maybe it's a tension with a rope, or maybe I'm pulling it by holding onto it. It doesn't really specify, but in any case, there's force pull. And the question is force pull, or why don't we just, for simplicity, just call this F. How big must F be? Okay, the next thing I'm going to do is I'm going to draw a free body diagram. So I have force forward, I have force friction backward, force normal upward, and gravity, aka mg, downward. Okay, so we want to know what F is right at the point where you've stretched the spring. Oh, actually, I do know what I'm pulling on it with. I'm pulling on it with a spring. Force, I'll call that force spring. Force spring. Okay, so I'm pulling on this box with force spring. So right when the spring begins to move, or the box begins to move, so basically I stretch, and then it just starts to move. So basically when that happens, right as it just starts to move, it doesn't have an acceleration yet. It's basically force friction is just barely canceling out force spring. And it's the maximum possible that the force friction can exert. This is static friction because because the box isn't sliding yet. So we can write it as the static friction, force static friction, I'll call that FF, is less than or equal to mu s F normal. In our particular case, because we want to know how hard you have to pull to get it to slide, this is actually an equal to, not just a less than or equal to. The reason being, well, if it were, is we actually need to pull it all the way until it moves. Before it moves, it might be less than, but right when it, we want to know the maximum, so right when it moves. Okay, so for spring is equal to mu s Fn. Oh, well, that begs the question, what is Fn? So doing the sum of forces in the y direction, we get force normal minus mg equals 0. There's no acceleration in the y direction, so we just get force normal minus mg equals 0, aka force normal equals mg. Hence, force friction is equal to mu s mg. Okay, but we also know that force friction, by the sum of the forces in the horizontal direction, we know that force friction is equal to force spring. They have to cancel each other out right when it starts to move. So we can write force spring is equal to mu s mg. Okay, so that gives us the spring force, but we're looking for how long the spring will be. So if you remember the spring equation is force spring is equal to K. I'm gonna leave out the negative sign because I don't have to worry about directions in this problem. We're pulling it forward, it's gonna move forward. I'm just gonna say spring force. this is be more detailed. The reason I'm leading off the spring, the negative, is I'm talking about the force that is acting on the box rather than the force, or the force that I'm acting on the box with, which is to the right, so it's positive. Okay, force spring is equal to K times delta X, the change in length of the spring. So that we can put these two equations together, plug in Fs from one to the other, and we get mu S mg is equal to K delta X, but I'm going to write delta X as L final minus L initial. So that thing there is delta X. Delta X is final length minus initial length. So initial length is the unstretched spring, final length is the stretched spring. Okay, the thing I'm looking for is the final length. So we can solve for that, this equation. You divide K to the other side, mu S mg over K. Do that in better handwriting. Mu S mg over K is equal to LF minus L naught. So add L naught to either side. To either side plus L naught. And we get that the final length of the spring when the box starts to move is L naught plus mu S mg over K, which is the quantity we were looking for. Okay, so in the second part of the problem, we are asked what will the acceleration be of the box be the moment after it starts slipping. So after it starts slipping, the frictional force gets smaller. So now the frictional force friction, is mu, zoom up on that, mu K F normal. The reason is it's sliding. Anytime you have something sliding, its frictional force is mu K F normal. You don't have to worry about a less than, because for kinetic friction, you always have it equal to. Okay, we can still use that force normal is mg. We derived that above. So we can say force friction is equal to mu K mg. I'm going to redraw the free body diagram. Force normal, force G, which is equal to mg. This is force friction. And force spring. Now the spring force is greater than the frictional force, so that the box is accelerating. Okay, how do we find that acceleration? Well, we use Newton's law. F equals ma. In particular, the sum of forces, or aka the net force, is equal to mg or ma. So I can write this as the net force. So moving us forward is spring force. Force spring forward minus force friction, because the friction force is pulling backward, is equal to ma. We can stick the friction force there, but the spring force, which we derived earlier, is still going to be the same. The spring is just after the box starts moving, the spring hasn't shrunk any, so its spring force will still be the same. So we can put in the spring force there, which happens to be mu S mg. We can stick in mu K mg for force friction, so we get mu S mg minus mu K mg is equal to ma. We can cancel the m's, and we find that the acceleration is equal to, and I'm going to rewrite this a little bit, mu S minus mu K G. All right, and that gives us our acceleration. We could check the units of it. The mu's are unitless, and g has units of acceleration, so that matches acceleration. We could check the units of this one up here. Length, yeah, length is length. That works out. Mu is unitless. Mg is newtons. K is newtons per meter. The meter comes up on the top and gets length, length, length. Okay, so units work for both of them. These are the two answers for this problem. Have a nice day.